Let's begin. Lecture 16. So I explained how to do the chi-square test of independence for a contingency table. Contingency table is a table of frequency. And the chi-square test uses the difference between the observed value and the expected value. And from this, it calculates some kind of a test statistic and uses that to determine if there is any relationship between the columns and the rows. Now let me explain how to get the expected value. So in many questions you wouldn't be given these expected values and you will have to find them. And the way you get it is, see, if this 111 was, if every one of these were blank, totally blank, and you were just given the row total and the column totals here and the total, what would you be filling in this here if you thought that there was no difference between the columns or the difference between the rows? What you would do is, you know that out of 839, 298 out of 839 would belong to this first column because 298 out of 839, right? But then among those, 255 out of 839 would belong to the first row, right? So you multiply these, and that would give you 90.57, right? So let me demonstrate that here. So if you had 839 times 298 divided by 839 times 255 and then divide by 839 again, that result will be 90.5721, which is why you see this 90.57 there. Okay, and eventually you do this for every cell in the raw data, and you get these values. Okay, so hopefully that did make sense. That gave you 90.57. Now, the question here is the number of hours volunteered independent of the type of volunteer? So it's like, is there some kind of trend? I mean, just looking at the raw data, it looks like the non-students, students who are not in college, seems to be spending more 4 through 6 hours. You see that this number is a lot bigger than the other two, right? Whereas the other numbers seem comparable. So you kind of see that, oh, maybe students who are not in college, uh, they may have more time to devote to volunteering, so maybe that's what's happening, right? But in order to address that, whether this is really statistically significant, you have to use the chi-square test. And the way you do it is by first taking the differences. Oh, no. So I should start with the null hypothesis and alternative hypothesis first. Okay, so remember, for the hypothesis testing of mean or testing of the proportions, the null hypothesis either mu equals to a number, or in terms of the proportion cases, p equals to a number. That's always the way that the null hypothesis, the H0, is formulated. However, when it comes to chi-square test of independence, H0 is always that the rows and columns are independent. Okay, and the alternative is that they're not independent. You get it? Okay, so H0 is independent, H1 is dependent. Okay. It's always for this chi-square test of independence. All right, then our test statistic is the following. You subtract the number observed minus the expected value. You square the difference, and you somehow have to normalize that by dividing by the observed, the expected value. So you divide by the expected value, and you do this, and you do it for how many? 9 values. So it's a lot to type, so I just da. But you know what I mean, right? So you just take the difference and divide, take the square of the difference, and then you divide by the expected value. And if you do that, we get the 12.99. And if this is big, then we say, oh, there's something off. I think there is a genuine dependence among the thing. They're not totally independent. Okay. If this number is not big enough, then we say, well, this doesn't really prove that somehow the being a non-student or student changes the way you volunteer. Okay. It doesn't mean that there is no effect. It's just that it just means that our data is not strong enough to prove it statistically. Okay. All right, so then here's a formula for the degrees of freedom. For the chi-squared, you always need to calculate the degrees of freedom, just like the t-distribution. And the formula for the degrees of freedom for chi-squared test of independence is the row number minus 1 times the column number minus 1. See, I have community college, four-year college, non-students, so you have 3 rows. So 3 minus 1. Times I have the 1 through 3 hours, 4 through 6 hours, 7 through 9 hours. So that's, again, 3 columns, and you subtract 1. You multiply these two, and we see that the degrees of freedom is 4. Now, what this is really saying is the following. See, if you're already given the row totals and column totals, then knowing these 1, 2, 3, 4, 5 values, if you had 91, 150, 53, 61, and 48 already populated with the row totals and column totals given to you, then just by performing some calculations, you can figure out that it should be 111 here, 96 there, 96 there, 133 there. So, no, that's just degrees of freedom. Oh, sorry, I said it backwards. If you had the rows total, row total, and the column totals already given to you, and you're given 1, 2, 3, 4 values, these 4 values, then just by using the fact that there's a sum is 298, and if you know that 111 is here and 96 is there, to get the sum of 298, it better be 91 here, right? So this one, this one, this one, and this one, and this one, these 5 values will be determined by these 4 values. So you really have just 4 degrees of freedom. That's what degrees of freedom means. Okay. Why that affects the statistics is a lot harder, a lot deeper, so I can't really explain. But just remember that the word degrees of freedom means that it's the number of data points that are free to change without affecting the row total or column total. All right, now if you know the degrees of freedom, then you can use the chi-square table to find the critical value. And I handed out the chi-square table today. If you don't have it, it's up here, so take it. And as you can see, for degrees of freedom 4, and let's say we're using 5% significance level. Did I say this somewhere? I forgot to say that. Okay, so I should have stated that somewhere. Okay. test at 5% significance level. That should have been provided. Okay, significance level. Okay, so let's put that somewhere. Put it here as well. Put it here as well. Okay, so if you know that we're using 5% significance level, then we go to the 5% significance level with 4 degrees of freedom. So what's the value? It's this value right here, right? 9.49. So we see that it's 9.49. And it's like this. If in the if the table of values were just randomly fluctuating around the value that you would expect, then the difference squared divided by the expected value sum, the chi-square test statistic, can only be as big as 9.49 with 95% probability. Okay, and because 12.99 is above that level, you can see that this says that the difference between the expected and the observed is pretty big. And therefore, you can conclude, what can you conclude? There is a relationship between the rows type of sequence and columns, which is this is amount of hours volunteered. Okay. Yeah. So maybe I should have said that as well here. The number of volunteers, hours volunteered, depends on the type of volunteer. I think there's a better way to say it is there is a relationship between number of hours volunteered depends on the type of volunteer. Okay, so that's how you often formulate the alternative hypothesis. Being dependent means that there is a relationship between the two variables, right? Okay, so hopefully this example problem gave you a better idea of how the chi-square test for statistics works. But before we move on, let me show you how to do this with a calculator. It becomes actually quite easy if you use the calculator because it calculates the chi-squared and all these other things. So try to do this with me. What you want to do is first go to second, and you see this matrix here, second matrix. And then you want to edit matrix A. And let's just try this one that we just did, this one here, this data. So now this data is 3 rows and 3 columns, right? It's like 3 columns and 3 rows, excluding the totals. So if you exclude the total row and total column, it's 3 by 3. So I'm going to put 3 here and 3 there. And then you just enter all the values. So 111, enter 96, enter 48, enter 96, enter 133, enter 61, enter. Okay, 91, enter 150, enter, and 53, enter. Okay, so once you have the matrix ready, you can second quit. And then you go to stat, and then you go to test, And if you scroll up, you're going to see the chi-square test. Okay, so we're going to take the chi-square test, and we are going to put as observed as A, because we just entered our data there. And B is actually blank, right? But we don't care because the calculator will automatically populate that with the expected value. So we're going to choose the B as the expected. It doesn't matter if it has other values, it will just overwrite whatever that is, okay? And then we go down and calculate. And as you can see, you see this chi-square statistic 12.99 right here, right? And you also see that the p-value is 0.01, so that's really, it is less than the 5%. Do you agree? Right? The significance level that we were working with was 5%, so the p-value being less than 5%, it does mean that there is a statistical significance, right? Significance level determines whether your test statistic is significant or not. If your p-value is less than the significance level, then your test statistic is significant. If your p-value is above the significance level, then although it may look somewhat extraordinary, it's not that unusual, and therefore there is no uh, uh, sufficient evidence to reject the null hypothesis. Does this all make sense? Because we're using the same kind of terminology over and over again, whether it's the testing population mean or population proportion, or we're doing test of independence. It's always this idea of having significance level. And if you're going with a p-value, if the p-value is less than the significance level, we say we have enough statistical evidence to reject the null hypothesis. Yes, you have a question? Yeah. Uh-huh. Bigger, yeah. Uh, no, no. As I explained in the previous hypothesis testing, it's always equal for the H0. H0 is stated as mu equals the number or P equals the number. In the chi-square test for independence, is H0 is always independent. It doesn't have any value. It's either dependent or independent, and always the independent one is the H0 and dependent one is H1. Right. Now notice that in the previous cases when we had the mu equals to something and the alternative was either mu greater than a number or less than a number or not equal, depending on that, we had to choose what kind of test, right? We had the two-tailed test if it's not equal. We had the right-tailed test if it's bigger. If mu is bigger than a number, that's right tail, and then left tail if it's mu less than a number. Here, there is no such a thing. It's just simply, yeah, independent, dependent. It's like, so you only care if it's above some value or less than some value, right? So in that sense, this is easier actually, because you don't have to think about left tail, right tail, or two tail. Yeah. Okay. Right. So, but just to remember that p equals to 0.01 means that something that would happen 1 out of 100 times just happened. If we assume that the H0 was true. So that kind of says, it kind of makes you inclined to say, hey, I don't believe this result is true, assuming the H0. So we reject the null hypothesis and adopt the alternative hypothesis, which says, I think indeed there is a difference between the type of students and the number of hours volunteered. Okay. That, yes. Okay. The question is, what happens if p-value is greater than significance level? Then, uh, I mean, the problem is that if something happens with some probability, when do you say it's unusual? Is it when, let's say you have an event that shows like 7% probability. Is that unusual to you? Depends on the person, and actually it depends on the discipline. If you're doing biology research, a lot of times like 7% is good enough. Whereas if you're doing physics research, a lot of the experiments are so exact that if you have something like 5%, that's still not good enough. You have to go down to like 0.1%. Yeah, so it really depends on the discipline. And a lot of the sociology results, they would say that, oh, if your p-value is like, say, 15%, we still think that there's something going on there. Yeah. So the significance level is like the level you choose before you do the analysis to say that whether at what point you're going to say that this is unusual. That's what it is. Yeah. Okay, so the question is what to do when the p-value is above the significance level, and you said, do we accept the null hypothesis? And that's actually not true because you have to write the correct language here. Uh, if the p-value is above the significance level, you have to say we failed to reject the null hypothesis because we're not really accepting the null hypothesis. We don't know. It's just that if something very unusual happens, then we can say, oh, we'll reject it. Okay, we know that H0 is false, but we don't know if H0 is true if the p-value is bigger than the null hypothesis. It only goes one way, right? So this is often in the tests and quizzes. I would be asking what to write if in case when the test statistic doesn't fall in the rejection region, or the p-value is not below the significance level, and I'll ask you what to write. And when you write, if you say, therefore we accept the null hypothesis, that's wrong. Okay, you don't get credit. You have to say, therefore we failed to reject the null hypothesis. There's a big difference. Okay, all right. All right. So yeah, so we saw the result. Now let's do one more example. Yes. Okay. So we saw we saw one example. Let's try another one. Okay, so a math professor wanted to know whether assigning homework and also having quiz is more effective than just having homework only or quiz only. So he tries to teach the same course over 3 semesters. In one semester, he just assigns homework, no quiz. In another semester, he assigns quiz. He gives quizzes, but there's no homework assignment. Just like how I'm running the class right now. In the other semester, he assigns homework and then has quizzes, so the students are having more workload, right? And then got this result. And if you look at the result, it does seem to say something, doesn't it? Right? Actually, this is not a real data. Sorry, I just made it up. But let's say this hypothetically that this is what you got. So when we just had the homework, out of 114 students who took the class, 90 passed and 24 failed. And when it was just a quiz, out of 95, 75 passed and 20 failed. So you can kind of see that this is about, maybe the homework only is slightly better. I don't know. But then in the semester when the professor used both homework and quiz, about the same number of people passed because there were less people taking the course, but you see like half the people failing. So that seems like, oh, that seems to say something. Maybe that's gonna prove that I should always assign homework and give quizzes, and the professor wants to know whether this result is good enough to prove that there is a difference between which way you run the class. Okay. All right. And I forgot to say at 5% significance level. So let's try this. Okay. Now first, and we'll assume that we do this using just calculation one by one, and also the table. Let's see. How do you fill in this empty spot? How do you do that? So you do out of 298, 245 out of 298 belongs to the first column, and also 114 out of 298 belongs to the first row. So this first cell should be calculated this way, right? And since that these 290 cancels, it's more like 245 times 114 divided by 298. Let's put that into the calculator and see what that gives us. Okay, 245 times 114 divided by 298. 93.72. So we put 93.72. Okay, let me give you some time for you to figure out what goes here. So in the quiz and failed cell, try to figure out what goes there. What should you calculate to get the expected value in that cell? Did anyone get an answer? What goes in there? Who wants to answer? Yes. What did you get? 16.9. Okay. Let's see if so, yeah, that's right. It's 290. No, 298 times 53 out of 298 times, and then it's 95 out of 298. Right. So that's going to be 53 times 95 divided by 298. And let's see, 53 times 95 and then divide by 298. And you get 16.89, which is 16.9. Very good. Yeah, well done. All right. So if we do that for every one of these cells, you're going to get these as your expected values. Okay. Now, let's talk about the degrees of freedom. The degrees of freedom formula is number of rows minus 1 times number of columns minus 1. Now, how many rows do we have? Excluding the total row, it's homework, quiz, homework plus quiz. So there are 3 rows, right? How many columns do we have? 2, yes, because it's only passed and failed, excluding the total one. So passed and failed is 2. So that gives you 2. Okay, so that's the degrees of freedom. Now let's calculate the chi-square test statistic. So it's chi-squared is equal to, you have to do 90 minus 93.72 squared and divided by the observed, plus, and then you go to the next one, you do 24 minus 20.28 squared and divide by 20.28, plus you do that until you reach the very end, which is 9 minus 15.83 squared divided by 15.83. And you can kind of see that the numbers, these differences are not that much, right? It's only like 4 difference, and if you divide that by, even if you square, you divide by 20, it will be less than 1. So a lot of these numbers are not that big, except this one here. This difference is 6, about 6. 6 squared is 36 divided by 15. That's about 2 point something. So this right here will have the most contribution, and that makes sense, right? It kind of makes sense because the most peculiar number in this table seems to be that when the professor assigned both homework and the quiz, it was only 9 people failed. So that seems to be the standout, and that's why chi-square works. It produces a huge value if there's a big difference between the observed value and the expected value. And I actually have the value for this computed 5.1094. So let's say we put this into a calculator, 5.1094. Okay. Now, is this significant? So let's go to the table. Let me copy this over here. Oops. Copy. Let's look at this table. Let's look at this table. And because our degrees of freedom is 2 and significance level is 0.05, what do you see as the critical value? So chi critical value is 5.99. Okay. So at significance level 0.05 and degrees of freedom 2, chi critical equals to 5.99. Okay, so we got the test statistic as 5.1 and the critical is 5.99. What's your conclusion? What's your conclusion? Can we reject the null hypothesis or not? No, we can't. Okay? There is not enough evidence. So, yeah, because our test statistic, the chi-square value, is less than the critical value. So the difference is not that huge. That's what we're saying. So, therefore, there is not enough evidence to reject the null hypothesis. And you should also be able to formulate this again in the context of the word problem, which is that we do not have enough evidence to show that a different way of running the class affects the pass-fail rate. Okay? We don't have enough evidence because, I mean, the distribution, the data did seem to show something, but it wasn't strong enough. That's what it is. Okay? Yes.
So I'm still confused as to why we reject the null hypothesis because don't we need like probability to like a p-value?
So there are two ways to do hypothesis testing, and you're asking me why we didn't use the p-value, right? Uh, so first of all, we don't have the means to use the p-value here. If you use the calculator, you can find the p-value, but from this table, you can only find the critical value. So that's why we didn't use the p-value. But there are two ways to draw statistical inference in a hypothesis testing. One method is to determine the rejection region by the critical value, and then see where your test statistic belongs to the rejection region or not. That's one method. Another method is to get the test statistic, and from there you can find the p-value, and from the p-value you see if it's above the significance level or below the significance level, and you draw conclusion that way. Okay, I'm using the former one. Okay, yeah. So the former one is what's called the traditional method, and that's actually the one that's uh, advised for many people, because when people are more focused on the p-value, they kind of end up doing fishing. They would like do experiments, different experiments over and over again until they kind of see which one generates somehow the low p-value. Because if you do it a lot of times, sometimes you get p-value or low p-value by chance.
So is
Yeah.
this one kind of like reverse of p-value? Like if the chi-critical is larger than the significance value,
So the question
then
is this like a reverse of p-value? Actually, uh, there's some truth to what you're saying, because to get the critical value, you take the significance level and you kind of do the inversion of the distribution. So uh, in the other case, when we are doing the testing for population mean, uh, to get the critical, you always do the inverse norm or inverse t to get the critical. You put inverse norm or inverse t applied to the significance level in some way. Okay, it depends on the type of tails, two tail, left tail, right tail, but that's what you use. You use the inverse function. Whereas if you want the p-value, you take the test statistic and plug in the test statistic into the CDF function. So there is a chi-square CDF that you can also use. Maybe I should show that as well. If you want the p-value, this is what you can do. It's let's see, you can do second distribution, and then you can go to chi-square, not the PDF, but CDF. And the lower is always 0, and the upper is 5.1094, and degrees of freedom is 2. And if you paste this, you get 0.92228, and 1 minus that value is the p-value. Now you don't have to know. Oh, sorry, 1 minus 0.92228. Now you don't have to know this one, but all I wanted to say was that indeed, when you want to get the p-value, you have to apply the CDF function. When you want to get the critical number, you have to apply the inverse function, inverse of the CDF function. So it could be like the inverse norm or inverse t, or this table. This table really gives you the inverse. Okay, for a given degrees of freedom and significance level, it's really giving you the value that's inverse. Yes.
So the x squared value has to be greater than the critical value in order to reject it.
Yes. In the chi-square test for independence, you always reject the null hypothesis only when your test statistic is above the critical value. Okay, if it's not, then you fail to reject.